Okay, so now we're going to turn our attention to the electron. And as it turns out, if we understand a lot about the properties of electrons within an atom, we're going to be able to figure out a lot of the reasons why atoms react the way they do, why they form specific ions in the fashion that they normally do in a chemical reaction. So right now we're really going to focus on the electron. And it turns out that before we discuss the electron, we should actually start talking about light, because as we're going to see, there's a very important aspect about the interactions of light and electrons that enable us to figure a lot of information out about the electrons within atoms. And of course, light has wave-like characteristics, so it's going to be good for us to discuss some of the properties of waves so that we have a better understanding about how light operates. Some of the things that we're going to want to discuss within a wave are, of course, the wavelength, which is the distance between any 2 points on adjacent waves to any 2 exact points. So if you measure the distance from a crest of a wave to another crest of a wave, that can be a wavelength. You can also measure that same distance from the 2 minima of adjacent waves, or even say the back edge of one wave to the other back edge of the adjacent wave. That will all give us the wavelength, which we abbreviate the Greek letter lambda. If we say that this wave is propagating in the x direction from left to right, if we measure the distance between the axes that is propagating and to the height of the maxima, or even to the distance from the axis to the minima, what we are measuring there is the amplitude. Now, what we're going to want to see is, of course, what those 2 measurements imply. Okay, and it turns out that if we measure the wavelengths of several different forms of light, it turns out the wavelength for visible light determines what color we see. It turns out that red colors have longer wavelengths than, say, yellow colors, and blue, indigo, and violet have the shortest wavelengths, and again, distance from 2 exact same points from adjacent waves. So when we measure the distance between 2 exact points on adjacent waves, the wavelength, that can determine what color of visible light we're seeing. The amplitude actually can give us information about how bright or how dim a light is. Okay, what we can see here is that the higher the amplitude, the brighter the light source will be. A very dim source will have a low amplitude. A brighter source will have an increased amplitude. Okay, so one of the things we're going to want to discuss, of course, if we measure these values, what types of units will we have? Well, it turns out that wavelength, because we're measuring distance, it's going to have units of distance, perhaps meters or nanometers, centimeters. It turns out that, as we'll see, depending on what type of region of the electromagnetic spectrum we're measuring, certain units are going to make a little bit more convenient. Okay, amplitude can have units of candela, CD, if this were a physics course. We'll see that this is also going to be a really good indication of how many photons a source is emitting, and we'll talk about that next, or shortly. Okay, it also turns out that if we want to discuss waves, another good property that we're going to need to measure is, of course, frequency. Frequency is a measure of number of waves that pass a point over a given period of time. So if you were to be looking out in the ocean and seeing ocean waves, if you counted how many waves passed say a buoy, over a certain period of time you would be calculating the frequency. So what type of units would we want to measure frequency with? Okay, well, we're counting waves as a function of time. We actually refer to waves more often as cycles. So cycles per any unit time, let's say second, could be used. For whatever reason, a lot of times cycles sort of is not given. So oftentimes units for frequency will just be 1 over seconds or reciprocal seconds. And reciprocal seconds is primarily what we're going to use in this course, but we'll also see that it can also be listed as hertz. Hertz is a unit that's fashioned after reciprocal seconds, and that's, of course, the abbreviation for hertz. Okay, now it turns out that because the speed of light is constant, 3.0 times 10 to the 8th meters per second, it turns out that if we know the frequency of light, we can calculate the wavelength. And we'll go over some of those calculations shortly. The speed of light is a constant, 3.10 times 10 to the 8th meters per second, which is, of course, is very fast. And here an image from your textbook illustrates how much faster the speed of light is, say, than another speed of a different wave, such as sound. If you've probably experienced this at some point in time, you might see some lightning or see the light emitted from lightning nearby, and then at some time later you'll hear the sound of the thunder. You hear the thunder second, and sometimes quite a number of seconds after you see the light, because the speed of light is so much faster than the speed of sound, 3.0 times 10 to the 8th meters per second, and sound has a speed of 340 meters per second in air, much slower, orders of magnitude slower. Okay, so as we said, if we know the wavelength, we can calculate the frequency because the speed of light is a constant, and vice versa. If we know the frequency, we can also calculate the wavelength. If we just take a look at the units, we can derive an equation for this. Okay, we know that the speed of light, c, has units of meters over seconds. So if we multiply the wavelength times the frequency, which has, we abbreviate with the Greek letter nu, we would be multiplying units of meters times reciprocal seconds, 1 over seconds, and so that, of course, gives us units of meters per second. So from this equation, we can rearrange it to solve for frequency if we know the wavelength, or we can rearrange it to solve for wavelength if we know the frequency. And from this equation, and as we'll talk about a little bit longer, or a little bit more in detail next, we can see that the frequency and wavelength of light are inversely proportional. As the wavelength of light goes up, the frequency goes down.